I have a video here to introduce our next major topic. We're going to talk about this for a couple weeks, and that is sequences and series. So the first thing I'm going to do is talk about why these are important to us in calculus. And then I'm going to review some of the definitions and notation that we use when we're working with these things. And this is something that you saw in algebra. So think back to Calculus 1. One of the problems that we do is construct linear approximations to functions. An example of a problem like that is the following. We want to find the tangent line to sine x at x equals pi over 3. I think you probably remember the steps. So here's what we end up with as our final answer. That's the equation of the tangent line. And if we graph the function and the tangent line, we can compare them near the value pi over 3. So we might want to ask, is this line a good approximation to our function? And the answer is it depends. Yes, it's a good approximation as long as we're close to pi over 3. But if we get far away from pi over 3, it's not good. It's terrible. The way we get this approximation is by using these two properties. So our straight line and our function have the same y-coordinate, and they also have the same derivative. That's how we find the slope of the line. We use the derivative of the function to do this. We're going to extend this idea. In Calculus 2, we do a new type of problem. Instead of a straight line, we're going to look for approximations that are parabolas or cubic functions, or some other polynomial function involving powers of x. Here's an example of our new problem. We want to find a quadratic approximation for the same function, f of x equals sine x, still near the same value pi over 3. When we build these approximations, we're going to use the following properties. These first two are familiar. This is how we find the tangent line. And for the tangent parabola, we're going to have to add one additional property. We want our approximation to have the same second derivative as our function, again at the value pi over 3. So for this particular problem, the quadratic approximation that we're going to come up with is this. And we're going to look at the details of how to find this in a couple days, but for now I just want to plot the approximation that I found. So here's the graph. You can see the parabola in green. And the question we want to ask again, is this a good approximation? To answer that question, let's compare the tangent line and the parabola that we just found. So here are those two functions, and we see the quadratic approximation, the parabola, is much better than the linear approximation. And what we mean by this is it's close to the original curve over a larger range of x values. Now the same idea extends to powers higher than just x squared. We can have a cubic function. So here's the cubic approximation for the same problem that we've been talking about. Building these approximations is one of our major goals over the next week or two. And before we get into the details of that, we need to review some of the basics, things that you learned in algebra about sequences and series. We're going to start by talking about sequences. A sequence is a list of numbers. Here's one example. This list of numbers is the list of perfect squares. The 3 dots on the end indicate that the list goes on forever. We can find a square for every number. When we're talking about sequences, we have some notation that we use to refer to the numbers in the sequence. So we can refer to each number with a subscript, saying a sub 1, a sub 2, and so on. We can represent the same sequence in this way. We have a sub n, and we show that n is going to be any number between 1 and infinity. And finally, if the context is clear, sometimes we just write the following. So a sub n, and the fact that we put it in curly braces means that it's a sequence, a list of numbers. In each of these notations, we have that small number n. It's called the index, and it refers to the position in the list. So if we look at our sequence of perfect squares, we can say that a sub 2, that's the second number in the list. That value is 4. And a sub 10 would be the 10th number in the list. The 10th perfect square is 100. Some of the sequences that we work with are going to be given by formulas that use this index. For example, let a sub n be the sequence with terms given by the formula a sub n equals n cubed plus 1. We're going to plug in each value of n to find the terms in the sequence. Here's our first value. So for the formula n cubed plus 1, I put in n equals 1, and then I simplify to get 2. A similar step gives me the second value in this sequence. I insert 2 into the formula in place of n and then simplify the result. The answer is 9. We can get the rest of the terms in this sequence following exactly the same process. So here are the terms a sub 3 and a sub 4. Once we get this answer, there are a couple different ways that we can write it. So we can just refer to the whole sequence a sub n. We can refer to the sequence using the formula that we were given. Or we can actually write out the list of numbers. And again, the 3 dots at the end of that list indicate that it continues forever. Let's take a look at another example using a formula to come up with a sequence. What's new in this example is the power of minus 1. That's something that we're going to see a lot in problems coming up. Again, I want to calculate some terms of the sequence by plugging in values of n. Here I plugged in n equals 1. We simplify the result and we get negative 1/2. The next term in my sequence, b sub 2, I put 2 in place of n, and here the answer is 2/5. Notice that minus 1 squared gives me positive 1, and so this term of my sequence is positive. The same idea gives me any term that I want to find. So here is b sub 3 and b sub 4. Once we get this answer, we can write it in a few different ways. So here are some ways that we can write the sequence that we're discussing. Notice that in the list of numbers on the right, we have a pattern of alternating signs, minus, plus, minus, plus. This kind of alternating sequence of positive and negative numbers is going to be something that we see again in a couple days. So those last 2 problems, we were given an explicit formula to find our sequence using the index n. There are other ways that sequences can be defined. So sequences can be defined using a recurrence relationship. Here we have a formula, but it uses the value of previous terms in the sequence, not the index number n. Here's one example of a sequence of this type. Notice that each value in the sequence is defined using previous values. So a sub n plus 1 is found using a formula involving the previous number in the list. Let's see how we use this relationship to find some terms in the sequence. The first term, a sub 1, that equals 1. That's given to us as a fact in the problem. Now for the next term, we're going to need to use the formula. Here's a sub 2. And to find a sub 2, I have to plug in the value that I found on my last step for a sub 1. So I did that. This answer simplifies to 3. And we can find any term in the sequence using the same relationship, we build on what we found at the previous step. Here's a 3 and a 4. Another example of a sequence defined using a recurrence relationship is the following. The formula is f sub n plus 2 equals f sub n plus 1 plus f sub n. Here are the first few terms in this sequence. So f sub 1 is given to us in the problem, so is f sub 2. Once we get to f sub 3, we use the formula. So I have to use two values here. I plug in the numbers that I have from my previous step, and the answer simplifies to 2. We can find all the values in this sequence using the same relationship. Here are the values up through the 6th number. This particular example has a name. It's called the Fibonacci sequence. It shows up in a lot of different applications, so some of you are going to see this in future classes. All right, that's a review of sequences. I think those things should be familiar to you from algebra. And in calculus class, we're going to take an additional step. We talk about limits, and so for a sequence, we want to discuss the limit as n goes to infinity. When a limit exists, it meets the following definition. So the terms of the sequence are getting closer and closer to some finite number. We'll call it L. And if this is true, then we say that the sequence converges, and we can write the limit using the following notation. If we have a sequence where this is not true, then we say that the sequence diverges. Let's take a look at an example of a limit of a sequence. So here we have a sequence defined using a formula in terms of n. And we use this formula to find the first few terms. Here's what I got. And now we're going to graph it and take a look at the pattern, see if they are approaching a finite number. Here's a graph of the first few terms of this sequence. And we do see some sort of convergence. It looks like those values are approaching 0. For right now, we're just going to look at graphs. We're going to come back to this problem in our next class, and we'll take a look at the algebra behind this limit. Now I want to move on and discuss another type of sequence. Here's our next example. So we have a sequence given by a recurrence relationship. We can use this formula to find the first few terms. There they are. We want to know what happens as n goes to infinity, and so I graphed the terms that I found. Here's the picture. And in this example, the terms of the sequence are not getting close to a finite number. It's growing forever. So we could say the limit is equal to infinity, or we could say the sequence diverges. There are other things that can happen, other ways that a sequence can diverge. The next example, I want to consider the sequence given by the formula minus 1 to the n. I used this formula to find the first few terms. There they are, and then I made a graph of these terms. When we look at this picture, we see that the terms of our sequence are not getting close to a single finite value. You could say they're getting close to 2 values, but that does not meet our definition of a limit, and so we would say that this example diverges as well. All right, that's all there is to say about the basic idea of sequences. We're going to get into some of the details in our next class, but now I want to move on and discuss the related idea of series. When we talk about a series, we're starting with a sequence of numbers and then we're adding them all together. And this means that we're adding an infinite number of terms One of the ways we can show that, when we have the plus sign with the 3 dots, that indicates that the addition process goes on forever. We also use a special notation called summation notation, that's on the right. And what this is telling us, we have j going from 1 to infinity, and for each number j, we're going to add the term a sub j to our total sum. Well, when we're talking about infinity, we have to be a little bit careful. So when we write down a sum of this type, it may or may not exist, and that depends on the exact sequence that we're adding. We're actually going to spend a lot of time on this exact question over the next few days. But for right now, I just want to point out it's not necessarily clear how to add an infinite group of numbers. If we have a finite set of numbers, we just write them. We set up addition and we add down the columns. But it's not really clear how we would add down the columns if we have an infinite list of numbers. So when I talk about some of the basics of defining these infinite sums, and to do this, before we define the infinite sum, we need to define a related family of finite sums. So I'm going to let S sub n denote the sum of just the first n terms in the sequence. We don't have an infinite sum anymore. We just have a sum consisting of n terms. N is some finite number. Let's take a look at an example of these partial sums. So in this example, I'm starting with the sequence a sub n, which is defined to be 1 over n. There's the first few terms of the sequence. And now we're going to define partial sums by adding the first few terms together. So in the first partial sum, I'm only going to add the first number, which is 1. My answer is 1. For the second partial sum, I'm going to add the first 2 terms in the sequence. So I have 1 plus 1/2. That simplifies to 3/2. And we can find any of these partial sums that we want. To find the third partial sum, I add the first 3 terms. For the fourth partial sum, it's the first 4 terms, and so on. We can do this for any number that we want. Here's one way that we could write the formula of the first n terms. I have 3 dots in the middle, indicating that the pattern I'm using continues with the same definition. Well, we know we can do this for any number n, and so we can use this process to construct a sequence. We're going to find all the partial sums, and then we're going to list them in order. That gives me the following sequence of partial sums. We know there's a couple ways we can write a sequence. So on the left, I wrote it using the notation S sub n, and on the right, I put in the numbers that we found on the last slide. Now we're ready to use this idea to define our new concept of infinite addition. We're going to define the sum of an infinite group of numbers by taking the limit of the sequence of partial sums. Okay, so we found that sequence S sub n on our last step. A couple minutes ago, we talked about how you take a limit of the sequence, and we're combining those two ideas together here to define the infinite sum of our series. Okay, I want to take a look at the following example. So let's consider the infinite series. The terms of this series are given by 1 over j times j plus 1. And I want to calculate the first 4 partial sums. So for the first partial sum, I'm just going to take the first term. That's the only thing there is. In this example, that's 1/2. To find the second partial sum, I take the sum of the first 2 terms. And in this example, that gives me 2/3. We use the exact same process to find all the partial sums in the sequence. Here's S3 and S4. So again, we're going to define our infinite sum as the limit of the partial sums. Using the numbers that we just found, we can set up the following sequence. I made a graph of this sequence, and from the graph I concluded that the limit of the sequence is 1. And so what this means for our infinite series, if we add up that infinite group of numbers, the answer to this particular problem is 1. Okay, so this was an example of what we're going to be talking about in our next couple classes. We're going to look at this idea of infinite series a little more formally next time that we meet.